we saw the gamma function come up in our discussion with the gamma distribution. So one of the, I would say one of the more interesting ones of being able to compute the gamma function for a value that's not an integer is gamma of 1/2. And the technique we're going to use to evaluate this integral is a technique that we're going to use in another integral here at the end of this video, which will also help us with the stuff we're going to talk about in the next section, in section 3.6. So let's look at this particular integral. So we have the integral from 0 to infinity of x to the minus 1/2 e to the minus x dx. This is gamma of 1/2. Remember, gamma of alpha was x to the alpha minus 1. So 1/2 minus 1 gives us the negative 1/2 here for the exponent. One of the things we'll notice about this particular integral is it's doubly improper. I can't plug the lower limit of integration in because it causes a 0 in the denominator. The upper limit of integration is infinity, so that also makes it improper. So technically we would need to split this integral into two pieces and handle two limits to be able to handle the integration limits separately, those improper limits separately. We won't worry that too much because all this stuff will come out in our actual evaluation of the integral. All right. So first thing we're going to do is we're going to rewrite this integral. We're going to make a substitution here. Basically, it's kind of like a trig substitution you did back in Calc 2. Instead of letting u be a function of x, we're going to let x be a function of u. Go the other way around. So we're going to put in u squared for x. And the motivation for that is it gets rid of that 1/2 power. Of course, if x is u squared, then dx is 2u du. So after we plug everything in, we get integral from 0 to infinity. Notice that limits of integration here won't change because if x is 0, u is certainly 0, and if x goes off to infinity, u certainly goes off to infinity. So we get this after we make our substitution. Notice that our u inverse, our u to the negative 1, and our u here will cancel each other out. And we just get 2 times the integral from 0 to infinity of e to the minus u squared du. Now, this integral is pretty, I'll say, famous in the fact that we can't do this by elementary methods. What I mean is, this particular function, e to the minus u squared, we cannot take its antiderivative and write it down as a function without using a power series. We can't write it down in what's called closed form. The main reason is because I don't have, you remember if I think about a w substitution now that I've already used a u, if I try to let w equal the exponent, I need a 2w out in front for the dw. I don't have that. So we're not going to be able to anti-differentiate this. So we have to be clever in evaluating this particular integral. All right. So let's call that value I. We're going to assume it exists. It does. The value of this integral definitely exists. We'll call it I. Then I squared is certainly squaring this integral without any issue. Of course, squaring just means we multiply something by itself. And now these are both definite integrals, so the letter doesn't matter. The variable that we're integrating with respect to doesn't matter. So I might as well call one of them x and one of them y. There's nothing wrong with doing that. And now, as far as the first integral is concerned, the y is a constant. And as far as the second integral is concerned, the x is a constant. So we can actually bring one constant in, one constant into one integral, and then the other constant inside the other integral, and make it look like a double integral, an iterated integral, like you've seen in Calc 2. Now, look at this exponent. We've got an x squared plus y squared up in the exponent, and that should make some alarm bells go off in your head. We can convert this to polar coordinates and see if we can evaluate it that way. Because remember, when we convert to polar, we get an r dr d theta for that differential piece. We'll get that piece that'll stick out in front that was missing before when we were doing trying to do the u substitution before. So r squared is certainly x squared plus y squared, and then we get to plug in the r dr d theta in for the dy dx. As this integral from 0 to infinity on both of these, this says that x is going from 0 to infinity and y is going to 0 to infinity. That's the first quadrant of the xy plane. So we can describe that in polar as r goes off to infinity, goes from 0 to infinity, but the theta goes from 0 to pi over 2. That would be the first quadrant of the xy plane. So notice that this part is a finite interval. The r is still an infinite integral, interval, sorry, but the theta is a finite interval. Okay, going back to the integral. I plugged in r squared for x squared plus y squared, r dr d theta in for dx dy. Okay. Anti-differentiate. Now, oh, we got a typo. This should be a negative r squared. As r goes to infinity, e to the negative r squared will go to 0. And when we put in 0, we get a 1 for that piece, so we'll get just a 1/2 for that that inside integral. And then if we integrate that from 0 to pi over 2, that gives us pi over 4. Now remember, that's the integral squared. So to find the integral, then we'll take the square root and find that we get square root of pi over 2 is that integral. And then if we remember for our gamma of 1/2, we had a 2 out in front of our integral. So that tells us that gamma of 1/2 is square root of pi. So that's kind of interesting, that we could actually compute this gamma value for something that was not an integer. Now it turns out that the halves are pretty much the only ones that we can do this for. If you try to do gamma of a third, you're not going to be able to find a nice expression for what gamma of a third is. You get decimal approximations all you want, but an actual expression is not possible, at least not thought to be possible. All right, so now we can define 1/2 factorial. That's kind of cool. So gamma of 3/2, remember, that's how gamma of n, remember we were defined as n minus 1 factorial. So gamma of 3/2 would be our 1/2 factorial. It's 1 less factorial. Well, gamma of 3/2 by our property of the gamma function is, remember, alpha minus 1, gamma of alpha minus 1. So 1/2 gamma of 1/2, we just calculated gamma of 1/2. So we get that the 1/2 factorial is square root of pi over 2. So that's kind of interesting. All right. We can use the same method to evaluate this doubly improper integral, minus infinity to infinity of the e to the negative x squared over 2 dx. This integral pops up in the normal distribution that we're going to study in the next section. Do the same thing. Let's let I be the integral, assuming that it exists. It does. We'll actually get a value. I squared, then I can do the exact same thing I did before. Write the integral twice, multiply by itself, change one of the variables to a y, and then recombine into an iterated integral. Now I can convert this to polar. Now again, x is going minus infinity to infinity, and so is y. So that's talking about the entire xy plane. That means the r is going to go from 0 to infinity, because we can certainly think about starting at the origin and going out as far as we'd ever want in any direction. The theta, however, is just rotating around the xy plane. Well, that means our theta is going to be 0 to 2 pi. All right, now let's do some anti-differentiation. Again, I've got a typo. This should be a minus r squared here. That should be the same exponent. Notice that we have a negative r squared over 2, so we don't have a 1/2 that pops out in front of this in this case. So we got minus e to the minus r squared. Putting in infinity, well, as r goes to infinity, e to the negative big is really, really small. So e will go to 0, e to that power will go to 0. Put in 0, we get 1. So we're just anti-differentiating d theta, which is just going to give us 2 pi for our answer. So we get that this particular integral is square root of 2 pi. So again, this integral pops up in our normal distribution section that we'll talk about in the next video.